You know, in particle physics, the whole game is smashing things together at nearly the speed of light to try and figure out the universe's biggest secrets. And the theories they use? They are incredibly precise. Until, well, they're not. Sometimes the very math that's supposed to predict reality just breaks.
Yeah, you heard me. It breaks. An equation that's supposed to tell you what's going to happen in the real world suddenly spits out an impossible answer: infinity. And you just can't have an infinite result for a real-world event. So how in the world do you fix a problem that is, quite literally, infinite? Well, let's find out.
Okay, so our story takes place inside some of the most powerful machines ever built by humans, places like Fermilab's Tevatron and, of course, the Large Hadron Collider at CERN. Scientists there are trying to predict what happens in these insane, high-energy collisions, like, say, when a W+ boson and a jet of other particles get created. But this is exactly where they hit a massive wall.
So this problem, it actually has a name. It's called divergence. And that's the official term for when a calculation, which is supposed to give you a nice, measurable, finite number, instead just explodes and heads straight for infinity. I mean, think about it. You can't have an infinite probability of something happening, right? It's a huge red flag that our mathematical model is hitting its limits.
Here's a great way to think about it. It's kind of like your camera's autofocus. It works perfectly on things far away, no problem. But what if you try to get it to focus on a tiny speck of dust that's literally on the lens, something infinitely close? The whole system just overloads. It doesn't know what to do. The math in particle physics is hitting that exact same kind of wall. So what's our speck of dust in these particle collisions? What specific thing is happening that's causing these, mathematical meltdowns? Well, it turns out the clues all point to one specific little particle. And the culprit? It's the gluon. You know, the particle that literally glues quarks together inside protons and neutrons. When particles smash into each other, they can shoot off extra gluons. And it's under very specific circumstances that this one little gluon sends all of our calculations into a complete tailspin.
Okay, so the math really breaks down into very specific situations. First, what's called a soft emission. That's when a gluon gets radiated with almost zero energy. And second, a collinear emission, where the gluon flies off in the exact same direction as another particle. In these super specific edge cases, our theory predicts an infinite probability, which is, just not possible in the real world. Okay, for those of you who want to see the math, here's a little peek at the problem. See that perp symbol in the denominator? That stands for the gluon's transverse momentum. Basically, it's sideways kick. Now, in those softer collinear cases we just talked about, that sideways kick gets closer and closer to zero. And as you might remember from math class, dividing by zero, that is a big no-no. The whole thing just blows up to infinity. So, if the math completely falls apart in these very specific, predictable ways, what do? I mean, you can't just toss out the whole theory, but an answer of infinity is totally useless. Well, it turns out physicists came up with something really clever, and honestly, pretty practical to get around it.
And they call it the transverse momentum cut. It's a fantastic name, right? Instead of letting the math just go haywire and run off to infinity, they basically draw a line in the sand and say, we're just going to cut out that problematic area from our calculation.
So here's how this cut actually works. It's really elegant. When a gluon pops out of a collision, its transverse momentum, that sideways kick, is measured. If that momentum is above a certain minimum value they've set, great, it gets counted in the calculation. But if it's below that cutoff, we basically just ignore it. We treat it as if it never even separated from the particle it came from. This neatly sidesteps the whole problem and stops the calculation from ever hitting that infinity zone.
It's kind of like being a referee in a soccer match. A ball blasted into the back of the net is obviously a goal. But what about a ball that just barely, maybe, grazes the line and is cleared away instantly? It's ambiguous. A referee might have a rule that says the ball has to cross the line with some kind of clarity to be counted. The transverse momentum cut is basically the physicist's version of that same practical rule.
Okay, this all sounds pretty clever, right? But, and this is a huge but, it raises a massive question. We've basically just cheated. We ignored the part of the math that was causing a problem. So, does this little mathematical fix actually produce a result that matches what we see in real experiments? Is this a real insight, or are we just making things up to get a nice answer? And wow, here is the proof, and it is absolutely stunning. On the left, you've got results from the Tevatron, on the right, from the LHC. Now look closely. Those individual dots,
That's the real, actual data measured from tons and tons of collisions. And that solid red line running right through the middle of them, that is the theoretical prediction made possible by using the transverse momentum cut. The match is, it's perfect. It's just incredible.
So there you have it. This isn't just some nifty mouth trick. It's a genuinely valid technique that lets our theories predict reality with just jaw-dropping accuracy. And it works across different colliders at different energy levels. The Infinity has been tamed.
All right, so we know the fix works. But to really get why it's so important, let's take one last look at the exact piece of the puzzle, the little term inside these giant equations that causes all the chaos in the first place.
This right here, this is the troublemaker. 1 over the transverse momentum squared. It's the same idea we saw before, just written with a slightly different symbol. Deep down, buried in all the complex physics, this simple-looking thing is the source of all that infinite madness. And the cut is what physically stops it from ever reaching zero.
So just let that sink in. The full equations, they're unbelievably complex. But the whole problem, the entire divergence issue, boils down to this one little relationship. And by carefully controlling this single term, physicists can turn an impossible, infinite prediction into one that matches the real world with breathtaking accuracy.
Okay, so let's wrap up our little detective story, shall we? The scene of the crime was the world's biggest particle colliders. The mystery was a calculation that kept exploding to infinity. The clues pointed to some very specific low-momentum gluons. The clever solution was the transverse momentum cut. And the final proof, the smoking gun? A perfect, undeniable match between the theory and cold, hard data. Case closed. And, this whole thing leaves us with a really fascinating, kind of deep question to chew on. We believe the universe runs on these precise mathematical laws. But to get the right answers, we sometimes have to introduce these very human, very practical rules, like just deciding to ignore things that are too hard to measure. So what does that tell us about the relationship between our perfect mathematical models and the messy, physical reality they're supposed to describe? It's a profound question, right at the heart of modern physics.